Hello everyone. This pre-lecture will focus on orbitals and quantum numbers. So sounds exciting. We're going to be moving from the Bohr model of orbits to this concept of an orbital. Okay? So the Bohr model worked really well for the hydrogen atom, but that's about it. Okay? And Bohr modified his model with Sommerfeld to add other things to it that we didn't go through in class. But we're going to move on and say, well, even though Bohr is the father of quantum mechanics, we need to go beyond that. Okay? So here's another person we need to focus on. And this is Verner Heisenberg. So and I spelled his first name with a lowercase w. Capital W. There we go. So that's Heisenberg, and you may have heard his name. He's very famous for, among other things, the Heisenberg uncertainty principle. Okay. So what Heisenberg said, and again, realize how science works. It's not like these guys are working in isolation. You know, Bohr is doing great stuff. We'll mention, maybe not in this one, we'll talk about gosh, I'm blanking on names now. Of course, we've talked about Einstein. Sommerfeld was a guy who worked with Bohr, and they modified the Bohr model. There's actually a model of the atom that's called the Bohr-Sommerfeld model. Sommerfeld was nominated, I believe, 70-some times for the Nobel Prize and never won it. Never won the Nobel Prize. But he did graduate the most PhD students who went on to get Nobel Prizes. Little trivia there. But anyway, we're going to talk about a number of scientists, and they all kind of built on each other. This was a really exciting time in the discovery of the atom. Okay, the atom's discovered, but actually figuring out how things really work inside the atom. So Heisenberg came along and said, we really can't, because of the wave motion of an electron. So just like we talked about light having both wave-like and particle-like properties, we have to do the same thing for other quantum particles like an electron. Okay, they don't behave like real-world particles. So because of this wave motion of an electron, we can't simultaneously know its position and momentum. Okay, and within momentum is velocity. Okay, so essentially the more we know about where it is, the less we can say about where it's going. Okay, and the more we can say what kind of path it's on, the less we know where it is. I mean, it's really bizarre stuff. So instead of talking about an orbit like Bohr did and saying the electron is on an orbit, okay, so this was from the Bohr model. Bohr, I can spell. That's an H. We have to talk about an orbital, a region of space where the electron is most likely to be. And typically we talk about probabilities. What is the likelihood that the electron 90% of the time will be in this region of space? We don't know exactly where it is, okay? But we know it's going to be somewhere in this region. And that's the concept of an orbital. Okay, so we're moving beyond the Bohr model. There are different types of orbitals, different shapes of orbitals. So this is what's called an electron density distribution. Okay, which again is a probability density. Where is the electron most likely to be? The darker the area, okay, so these are all kind of dots where the electron could be. The darker the area, the higher probability. So, I mean, you can see in here, certainly closer to the nucleus, this is higher probability. And as we go further out from the nucleus, say somewhere out here, certainly we see a lower density of dots. This would be a lower probability. Okay? And the region that has, and I didn't show this graph. It's in the lecture notes that are posted online. The highest probability of where we find the electron corresponds to the radius of the first Bohr God, I'm having trouble spelling Bohr. How is that? Bohr orbit. Okay, so Bohr actually, and we didn't do this calculation class, he actually came up with an equation to calculate the radius of his orbits, n equal to 1, n equal to 2, n equal to 3. And the highest probability of the electron in this 1s orbital, and we'll talk about what 1s means in a minute, actually does correspond to the radius of the first Bohr orbit. So Bohr really did some pretty cool things. So that's an s orbital. We're going to talk about different shapes of orbitals and where they exist in the atom. Now, more often, I got ahead of myself, the 1s orbital is really shown as a boundary surface rather than dots, because we don't want to have to draw dots all the time. So we're going to draw a boundary surface that, in effect, encases that 90% probability. Okay, so inside that surface, now this doesn't exist, orbital doesn't exist inside the atom. There's not a spherical case that holds the electrons. But we're just saying, if we were to draw a physical case around this spherical surface, around, it would encapsulate 90% of where the electrons are in, say, the hydrogen atom. Okay, so we typically draw a boundary surface. Now, here's the other shapes, and we're going to talk about where we see these in the atom. Okay, what orbits or energy levels? Okay, Bohr called them orbits. We're going to call them energy levels. We'll also call them shells, which is a holdover from the orbit, and we'll talk more about that. These are what are called p orbitals. And this will become important as we talk about, you'll notice there are 3 different p orbitals: px, py, and pz. Okay? And so anytime we encounter p orbitals, we're going to have them in a cluster of 3, what we call a subshell. Okay? So this cluster of 3, we would call this the p subshell. And that p subshell consists of 3 orbitals: px, py, and pz. 3 orbitals. All right? So keep that in mind. Anytime we, in any energy level or shell where we have a p subshell, when we say p subshell, we mean 3 different p orbitals: px, py, pz. Keep that in mind. We'll come back to that. Other type of orbital, d orbitals. So this would represent the d subshell. So anytime we encounter d orbitals, and we'll talk about when we encounter these, because they're not, turns out they're not in the first level or the second. It's not until we get to the 3rd shell or the 3rd energy level. We'll talk about how we know that. The d subshell consists of 5 different d orbitals. Okay? I'm not going to ask you to memorize the symbols, but the symbols make sense. The dyz up here, the orbitals are in the yz plane. xy, they're in the xy plane, and so on. xz plane, and so on. They all kind of look similar with this 4 lobes of electron density. So we call those lobes. Those are regions of electron density. So that would be a lobe. Okay, regions of electron density, except for the dz square, where we kind of have this donut of electron density in the middle. Okay, but in general, know the shape. The typical shape of a d orbital is 4 lobes, kind of a flower, if you want to think of it like that. And the last type of orbital I expect, one thing I want to point out again, this d subshell again is 5 orbitals. All right, 5. Anytime we encounter a d subshell, we mean d subshell, 5 different d orbitals. Okay, and the last subshell I expect you to know, and again, you don't need to know the labels, but you need to know the f subshell, particularly how many orbitals you have. Anytime we encounter an f subshell, there are, as you can see, 7 of these. Okay, so let's scroll back here and let's look at our subshells. The s subshell. Okay, there's only, when we have an s subshell, there's only 1 orbital. Okay, so anytime we encounter an s orbital, there's only 1 of them. That's it. P subshell. There will always be 3 of them, px, py, pz. You should know that. That's easy to know those symbols, px, py, pz. Anytime we encounter a d subshell, there are 5 of them. dxy, dxz, dyz, and so on. Anytime we encounter an f subshell, there will be 7 orbitals. Okay? And they vary in shape. You'll notice that some of them have 8 lobes, like these guys down here have 8 lobes of electron density. We see some of these donuts of electron density and so on. Okay? But know how many orbitals in an F subshell. Okay, let's see if I can get my mouse to actually work here. And the last part of this pre-lecture, now that we know the shapes of the orbitals and how many are in a subshell, is we're actually going to use a numbering scheme that actually comes out of all this. When Bohr proposed his model, we had the first quantum number. We've already talked about n. That was, in the Bohr model, that was his orbits. N equal to 1, n equal to 2, n equal to 3, and so on. First orbit, second orbit, third orbit. We didn't do the Bohr-Sommerfeld model, but Bohr and Sommerfeld actually based on looking at the fine structure and emission spectrum. So when we looked at emission spectrum in class, we just looked at the prominent lines. But if you actually have a better spectrometer, you can see all these other lines as well. And so they actually proposed 2 more quantum numbers based on all these other lines. And they proposed, God, my mind in the morning doesn't work so well. Non-circular orbits, elliptical orbits would be a better term. Okay, so they proposed all these other different orbits and different things to explain these lines. And so they actually proposed 2 more quantum numbers. And then there was a 4th one that dealt with the spin of the electron. And then all of this came together in Schrodinger's wave equation, which we will mention in class as well. But what we call this n value, it's the principal quantum number. It's going to correspond to the energy level. N equal to 1 will be lowest energy. So this will be increasing energy. Okay. N equal to 2 will be higher. N equal to 3 will be higher, and so on. Now, as we go up, the levels get closer together, and that will become important later on. Okay. We also call these energy levels as a holdover, as I've mentioned, we call them shells as a holdover from the Bohr model. Okay. A shell like an orbit. Okay. So if you hear me say the first shell, the second shell, the third shell, we mean the same as the first energy level, second energy level, and so on. Okay? And again, read this second bullet. The larger the n, the greater average distance the electron is from the nucleus. Okay? So not only is it a measure of the energy, but it's a measure of distance from the nucleus as well. Okay, now the second quantum number, haven't done this yet, has the symbol L. It tells us the shape of the orbital. Tells us the shape. We've gone through the shapes already, right? S, P, D, and F. You need to know those shapes. Okay? Memorize. I don't ask you to memorize much in this class, but you have to memorize these quantum numbers. L equal to 0. That is an s orbital. L equal to 1. P, L equal to 2, D, L equal, sorry, that shouldn't be on that line, but there it is an F. You need to know that. Okay, in the next slide, these are the lecture notes that are posted online. The next slide just sums this up. Okay, so memorize this. Okay, it's not that hard, except we start with 0. A lot of times students want to say the S is 1, P is 2. No, we start with 0. So L equal to 0, S. L equal to 1 represents P orbitals. L equal to 2, D. L equal to 3, F. Okay? Now remember, keep in mind the subshells and how many orbitals are in each subshell, because we'll get to that with the next quantum number. But this one just tells us the shape. Do we have S orbitals, P orbitals, D orbitals, or F orbitals? Now, let's go back, because we need to know what orbitals are in each shell or energy level. Okay, so in the first shell, what orbitals are in there? In the second shell, what orbitals are in there? In the third shell, what orbitals are in there, and so on. How do we know that? Okay, well, we can do that using a simple equation. The allowed L values, okay, for a given n. Okay. And remember, n is the shell or energy level. The allowed L values, and it says it here, although it's hard to see because it's split, go from 0 up to n minus 1 integer values. Okay, so what that means, they always have 0. So it doesn't matter, n equal to 1, n equal to 2, n equal to 3. We're always going to have L equal to 0. Okay, so every single energy level and every single shell has L equal to 0. And what does that mean? It's right here. Every single shell has an S subshell. Okay, so every single energy level, n equal to 1, n equal to 2, n equal to 3, has an S subshell. Okay, now we're going to call them differently. The first one we're going to call, I'm going to write it on this side, 1s, 2s, 3s to represent the n value, but there's always an s orbital. Now, in the first shell, is there anything else? Okay, so if n equals 1, is there anything other than an s? Well, the valid values are from 0 up to 1 minus 1, n minus 1, which is also equal to 0. So in the first shell, all we have is the 1s. That's it. So remember, we're closer to the nucleus. We can't put too many electrons there. And we're going to find that any one orbital can only hold 2 electrons. So very close to the nucleus, we can't have many electrons. We only have one orbital. Now, we go further from the nucleus to n equal to 2. Well, we know we have 0, but it's also going to go up to 2 minus 1, which is equal to 1. What does that represent? P orbitals. So we also have L equal to 1 in the second n value, and that represents a p orbital. How many p orbitals are there? There's 3. There's the p subshell. We'll talk about that in a minute. So in the second shell, we add another type of orbital. We add the p orbitals. Okay. What about the third shell? Well, again, we have 0 up to 3 minus 1, which is equal to 2. Now, we're going to include the integer values in between. So we're going to have 0. We're going to have the 1, which is in between 0 and 2. So 0, 1, and 2. So in the third shell, we're going to have L equal to 0, L equal to 1, which is P, and L equal to 2, which is D. Okay, so all of this here is the third subshell. So third shell. Each of those is a subshell within that, the 3s, the 3p, the 3d. All right, so as you can see, as we move further from the nucleus, we need more regions of space where the electrons are. Okay, more regions of space. And remember, in the s subshell, we just have one orbital. The p subshell, 3. The d subshell is 5. We've already talked about that. So in that third shell, look how many orbitals we have total. We have 9. Okay, so more orbitals, more regions of space where the electrons can exist. And we're going to go on later and look at each orbital holding 2 electrons. Okay, second shell has 2 subshells. The s, which is 1 orbital, the p, which is 3. So in the second shell, we have 4 orbitals. Each can hold 2 electrons. And in the first shell, we just have the s subshell, which is 1. Okay, so what you should see, one, you should know what these numbers tell you, okay, quantum numbers, but you should see we add a new type of orbital for each energy level, for each shell. N equal to 1, we just have the s. N equal to 2, we have the s and the p. And we call those the 2s and the 2p for the second shell. In the third energy level, we add the d. So we have the 3s, the 3p, and the 3d. Okay, get the idea? And why don't I write here, let's do n equal to 4. Our allowed L values are going to go from 0 up to n minus 1, which is equal to 3. So in the fourth shell, we're going to have L equal to 0, L equal to 1, L equal to 2, and L equal to 3. Okay, so we're going to have the 4s, the 4p, the 4d. Again, remember, know what your L values tell you. and L equal to 3. What is L equal to 3? That's the f orbital. So in the fourth energy level, we finally add the f orbitals. How many orbitals in each shell? S always is 1, P is 3, D is 5. How many for F? 7. So look how many orbitals total are in the fourth energy level or shell. 4, 9, 16 total orbitals. Each can hold 2 electrons. That's 32 electrons. Wow, lots of stuff. So again, we're moving further and further from the nucleus. There can be more electrons in that region of space. All right, there's our L values. Keep that in mind. Make sure you know where they come from. Now, we've already talked about the subshells, and that's where the third quantum number, m sub L, and these will always be written in order N, L, m sub L. Okay? Describes the orientation of the orbital in space. Okay, so it represents the number, which we've already talked about. The number of orbitals of equal energy. In effect, the number of orbitals in a subshell. And you already know this. You know the P subshell is 3. You know the D subshell is 5. You know the F subshell is 7. You already know that. But these numbers will also confirm that. So these values go from minus L up to plus L, integer values. So for L equal to 0, which is the S subshell, what are the allowed m sub L values? The only m sub L value is 0. Minus 0 up to positive 0. It's just 0. That tells you there's only one orbital in that subshell. And we know that already. Anytime we have an s orbital, we just have one of them. L equal to 1 represents the p orbitals. What are the allowed m sub L values? They go from minus L, so minus 1, up to plus 1, but integer values, so that's going to include 0 in between. Look at the 3 numbers we have for m sub L. That represents 3 orbitals in the p subshell. We already knew that. But those are the numbers that tell us that. L equal to 2, those are the d orbitals. What are our allowed m sub L values? They go from minus L up to plus L. So minus 2 up to plus 2, but integer values in between. So minus 1, 0, and plus 1. How many numbers there? There are 5. That represents the 5 orbitals in the D subshell. Get the idea? Okay, so we already knew, we talked about how many orbitals in each subshell. This third quantum number confirms that, tells us that. Okay, and let's do L equal to 3 since I want you to know up through F. Okay, so the F orbitals, what are the allowed m sub L values? Okay, minus L up to plus L, minus 3 up to plus 3 with integer values in between. Okay, how many numbers are here? 1, 2, 3, 4, 5, 6, 7. 7 orbitals in F subshell. There you go. We've basically covered, we started out looking at pictures of the orbitals and saying, make sure you know in the S subshell there's only 1. Make sure you know in the P subshell there's 3, D subshell 5, F subshell 7. These numbers, the number of m sub L values, tell us that same thing. Okay? And we're getting close to the end of the pre-lecture here. So those are our quantum numbers. This table, again in the lecture notes, summarizes. This would actually be for n equal to 4. So you might want to go through. If you have n equal to 4, your allowed L values, we already did this on a previous slide, are L equal to 1, 2, 3. Remember, these go from 0 up to n minus 1. So those are your allowed L values, S, P, D, F. So in the fourth energy level, we have the 4s, the 4p, the 4d, the 4f. And again, we just went through these allowed m sub L values, which tells you you have a 4s orbital. There's only 1. 3 numbers there, 4p, there are 3 orbitals in the 4p subshell. D orbitals, there are 5 numbers there. In the 4d subshell, there are 5 orbitals. 4f, 7 numbers. 4f subshell, there are 7 orbitals. Total of 16 orbitals. Look at that. Nice, easy way to tell the number of orbitals in a shell energy level. It's just n squared. So this is n equal to 4. If we want to know the total number of orbitals, 4 squared, 16. We can add them up here, but very simply in the 4th energy level there are 16 orbitals. Each can hold 2 electrons for a total of 32 electrons possible. We'll do more later as we do electron configurations. And the last quantum number, again, when we write these, okay, they'll always be in the order n, energy level, L, shape, m sub L, the number of orbitals, or the orientation. Because if we just specify one m sub L value, say px is, we'll just for now say px is -1, py is 0, pz is +1. That would represent which of those 3 p orbitals you have, excuse me. And m sub s is what's now called the spin of the electron. Remember, I've said it a couple of times, but any orbital can only hold 2 electrons. Okay, and they will have opposite spin. That's the lowest energy configuration. So a spinning charge generates a magnetic field. We can think of, a clockwise and a counterclockwise spin. It's not quite like that, but it's, a quantum mechanical concept. But they do have different magnetic fields, and it's the lowest energy if the magnetic fields are opposite and cancel each other out. So the 2 spins of electrons will be designated +0.5 and -0.5. Okay, so there's your 4 quantum numbers, just like that. Now, let me give you an example. Okay, let's say we have a 4d orbital. Okay, give a possible set. So let's say give one possible set of quantum numbers for an electron in a 4d orbital. Okay, just one set. Well, 2 of the quantum numbers are fixed. That 4 represents your n value. It's a d orbital, so what's your L value? You've got to memorize this. L equal to 0 is S, L equal to 1 is P, L equal to 2, D. So those are fixed. Okay, now I'm just asking for one possible set, which means n, L, m sub L, m sub S. So our m sub L values, as you're probably thinking, well, they can go from -2 all the way up to +2. Okay, but we're going to write one possible set. So just choose one of those numbers to represent one of the 4d orbitals. Remember, there's 5 different d orbitals in the 4d subshell. We're just going to choose one possible orbital that electron can be in. And then that electron could either have what we call spin up, +1/2, or spin down, -0.5. Okay, clockwise or anti-clockwise. All right, so one possible set would be 4. Again, we write them n, L. Choose an m sub L value. Choose your favorite one. Let's say -1, and then choose a spin. That would be one possible set for a 4d electron. So an electron in a 4d orbital. Okay, this is n, this is L, this is m sub L. Now you could have written -2, you could have written 0, you could have written +1, +2, any of these m sub L values. And this is the spin, so you could have written -0.5. That would be a possible set. If I wanted to write another possible set, I could write 4, 2, that's fixed. Let's say +2 and -1/2. That would be another set. And other set. I should not try to write so fast. Okay, that would be another set, a possible set of quantum numbers for an electron in a 4d orbital. N equal to 4, that's fixed. L equal to 2, that's fixed. That represents a d orbital, 4d. But this is one of the 4d orbitals, +2 for m sub L. And here's one of the possible spins, +0.5 or -0.5. All right, last thing for the pre-lecture. let's write both sets of quantum numbers for the electrons in a helium atom. Okay, so look at a periodic table, and you will see that helium only has 2 electrons. So that's why we're going to write the 4 quantum numbers for each of those 2 electrons. Okay, now the 2 electrons are going to be in their lowest energy configuration, the ground state. So what's the lowest energy? N equal to 1. Okay, what L value is allowed in N equal to 1? Remember, it goes from 0, the allowed L value is from 0 up to n minus 1. So the only L value in the first energy level, or first shell, is L equal to 0. That's an s orbital. How many electrons can any one orbital hold? 2. So those 2 electrons are going to be in the 1s orbital. Does everybody see that? So the first orbital is the 1s. It's the 1s. Can hold 2 electrons. So those 2 electrons are going to be in that 1s. Now we have to specify the quantum numbers. Well, it's a 1s, so it's going to be 1 and 0, n and L. Okay? The other set is going to be the same because both of those electrons are in the 1s. What about m sub L? What is the allowed value for m sub L? I'm going to write it over here on the side. It goes from minus L up to plus L. So our L is 0, so it goes from 0 up to 0. So the only m sub L value is 0. Okay? There's only one 1s orbital. There's only one of them. That's it. Okay? So these quantum numbers are the same. Is that okay? Yeah, they're okay. It's okay because we're saying that both of those electrons are in the 1s orbital. These 3 numbers say 1s. Okay, first energy level, n equal to 1. Shape, L equal to 0, that's the s. There's only one of them, so they're both in the same 1, same m sub L value. What's the difference? What's the difference between those 2 electrons? They're going to have opposite spin. One's plus 1/2, the other minus 1/2. There you go. So the 2 electrons in a helium atom are in the 1s orbital with opposite spin. And those are our quantum numbers to represent that. Both in the 1s, opposite spin. Quantum numbers. I like quantum numbers. Students tend not to, because I don't think that students really want to memorize the rules as far as how you assign them. But think of it from both kind of a number perspective and know the rules. You have to know the rules. You have to know your L values. You have to know your allowed m sub L values. You have to know your 2 spins of the electrons. But also think of it from more of a qualitative sense, that in the first shell or energy level, we just have the 1s. And as we move up, we're getting further from the nucleus, so we need more orbitals. We need more regions of space for the electrons to exist in. So we get to the second shell, n equal to 2, the second energy level. And we have the 2s and the 2p. Okay, we add a new orbital each energy level. Now we go up to n equal to 3. We now have the 3s, the 3p, and the 3d. Okay, we've added the d in the third energy level. Now we go up to the fourth energy level. 4s, 4p, 4d, and now add the 4f. We need more space for the electrons. Okay, so think of it from that perspective too, instead of just saying, oh, I know the first energy level is just the s. The second is s and p. The third is s, p, and d, and so on. And then the numbers kind of then fall into place for you. Okay, so practice these. We'll practice more of these in class. And eventually what we're going to do is kind of what we did with helium. We're going to then start looking at what are called electron configurations to kind of show you where we're going, to say, let's actually write out a configuration of what orbitals are holding the electrons in, say, something like zinc or something like argon. Okay, what orbitals, the s and the p and the d, and how many electrons are in each one. Okay, well, that's what we're moving to. Okay, thanks for listening, and I will see you in class.